everyone, I'm going to talk about the application of the Hess law um, in some calculations. First of all, we need to know what does it mean by this Hess law. The Hess law is defined as the enthalpy. It is about the enthalpy. And since enthalpy is a state function, the change in enthalpy occurs when reactants are converted to products in a reaction is the same whether the reaction takes place in one step or in a series of steps. That observation is called as Hess law. Okay, let me explain it using some illustrations. Let's see, this is the A and this is the B, and it produces this AB. Okay, so this requires some sort of enthalpy. I'll call it as delta H1. Right. But so in this AB has been synthesized from a one step. But if it was synthesized like a first AB2 and then AB, so it has gone through two steps. But the enthalpy is a state function, therefore this delta H1 will be equal to the addition of those the energies or processes happen through these two steps. That means the enthalpy of formation of product doesn't depend on the path or the number of steps of that reaction. So that is known as that observation is known as the Hess law. So if I numerically says that delta H1 equals, if I say this delta H uh, 2 and delta H3, so then delta H1 equals to delta H2 plus delta H3. Let's look at this example. Given the following thermochemical equations, nitric oxide NO gas plus O3 gas gives NO2 gas plus O2 gas. The enthalpy for this reaction was given as negative 198.9 kilojoules per mole. Then we are given another equation, O3 gas goes to O2 gas. The coefficient for the O2 is 3 over 2. And the enthalpy for this reaction is given as negative 142.3 kilojoules per mole. The next reaction is the O2 gas changed to two single oxygens, and the enthalpy for this reaction is an endothermic value since it's a positive one. So it was given as 495 kilojoules per mole. So we are given these three reactions and the enthalpies for these three reactions, the heats for these three reactions. And we need to find the enthalpy change for this given reaction. NO gas plus O gas goes to NO2 gas. Let's see how we can solve this problem. We are going to use the principle that is discussed under his law. We are going to arrange these thermochemical equations in a way that the sum of those three equations will be resulted the desired equation. So we may need to change the sides, or we may need to add multiply or divide these equations. And then we add all these reactions together to get the desired enthalpy change. As an example, this was the first one. So I'll write NO plus O3 goes to NO2 gas and O2 gas. I just use the enthalpy as it was given. Next, the 3 over 2 O2 gas goes to O3. Okay, so it was 142.3 kilojoules. Then the O goes to the O2 and the enthalpy. Remember, this was given as in the other way. But now I have to change the side. So I just swap it and I change the sign of the the heat, uh, the uh, the heat change. So the positive becomes negative, or the sign of the heat will be changed as you change the direction of the reaction. So that is negative 247.5 kilojoules per moles. So when I add all these three reactions, O3 will be cancelled out with this O3, and there is one O2 and another half. Those two will be cancelled out with the 3 over 2 O2. So what I just get at the end, yes, NO and O single O and the NO2. Okay, that was the reaction. I was asked to find the enthalpy change. So when I add all these three numbers together, I get this value. Next, we are going to talk about the standard enthalpy of formation. The how we can define the standard enthalpy of formation. Yes, but we do not know a standard or an absolute method to find the standard enthalpy of formation of a reaction. But we will play, or will just arrange some other reactions, and we'll get the desired equation for the standard enthalpy of formation for a particular compound, so that the value is depend on the other reference values. Okay, what is this standard means? There are some standard conditions. So the standard enthalpy of formation is defined as the heat change which resulted when a 1 mole of compound is formed from its constituent elements in the standard states. Okay, as an example, if I look at this reaction, okay, so the standard, always the standard conditions will be symbolized by this superscripted the node. So the delta H node reaction, the standard enthalpy of reaction for this reaction can be numerically explained as just the standard enthalpies of these products minus the standard enthalpies of the reactants. So the standard enthalpy of the product C and multiplied by its coefficient plus the standard enthalpy of D multiplied by its coefficient, the lowercase d, and minus, now we are adding the standard enthalpies of the reactants. The standard enthalpy of A multiplied by its coefficient A, standard formation enthalpy of B multiplied by its coefficient. So we can calculate, basically, we can calculate the standard enthalpy of a reaction by subtracting the sum of the standard formation enthalpies of reactants from the sum of the standard formation enthalpies of the products. Okay, look at this. um, we need to find the standard enthalpy of reaction for this one. Ag plus aqueous is reacted with is allowed to reacted with Cl minus aqueous goes to AgCl solid. So we are given the standard formation enthalpies of silver plus, chloride minus, and the AgCl as the 1100 0.5 5.9 for the Ag plus, 2167.2 for the chloride ions, and 2127.0 kilojoules per moles for AgCl. So now we add the products and we add the reactants and we subtract the standard formation enthalpies of reactants from the standard formation enthalpies from products. Okay, so the product is the AgCl and these are the two reactants. We add those two formation enthalpies of those two reactants and we now plug their values and we find the answer as negative 65.7 kilojoules per mole. That is the standard enthalpy of that reaction for that the this reaction. So we do not have an exact way to find the standard enthalpy for this reaction, but we use the standard formation enthalpies of these products and the reactants, and we found the standard enthalpy for this reaction. Next, another problem, given the following information, calculate the standard enthalpy of formation for acetylene from its constituent elements. Let's first, what is the formation of acetylation? Formation of acetylene. Let's write the equation for the formation of acetylene. The standard formation always starts from the standard elemental levels from that compound. So I'll write the C2H2. It should be in the gas form. So what are its elements? Yes, carbon. The standard form is graphite and the standard form of hydrogen is H2 gas. So now I'll just balance this equation. This is the standard formation reaction for the acetylene C2H2. Now we are given these three reactions. Okay, so and we are given the enthalpies of these reactions. So what we should do? Let's add these two. Okay, and let's see whether what we can do. So we have to arrange these equations to provide provide the sum of those the addition uh, will equal to the desired equation, and we may need to reverse some equations or multiply it one or more equations. For any such change we should change the delta A of this or the enthalpy change of that reaction too. If we change the sides of the reaction, then the sign of the enthalpy change will change too. Or if we uh, multiply the whole reaction by 2, then you should multiply that enthalpy change for that given reaction by 2. Okay, so now I had to I added these three reactions, okay, and I got the desired reaction, and obtained the value for this reaction as 226.6 kilojoules per mole. So this is the standard formation of the carbon dioxide. This is the standard formation of water, and this is the reverse of the burning of the acetylene. So the burning of the combustion reaction, this is the reverse of the combustion reaction. So now you will see that the sign of the enthalpy value has also been uh, changed.